we are restarting the Bangalore probability seminar. We'll be running online for some time, and already we have this and 2 more talks. And for some time we'll be experimenting, at least we'll try with the format of, since it's online, we have the thing of picking and choosing speakers more easily. And we will try to have maybe 2 related talks, so that one talk can be a background or overview talk, and second can go into more details. This way it might be more easy for many people. And before we start, some rules. So any question today, since both Matthew and Shiva are speaking, one of them will be monitoring the chat when the other person speaks. So any question, first please post it in the chat. One of them will try to answer. If not, maybe I will interrupt Shiva, or even Matthew might interrupt Shiva, and vice versa for Matthew, and we might ask them questions. And as said, at the end of the talk, again, well, then we can unmute everybody and ask questions. This is just to streamline the questions instead of people interrupting every few minutes. It might be easier for the speaker this way. And so again, I will put up the link for the slides. People who haven't seen the email can access the slides from the BPS website. At least Matthew's slides are there. Shiva's, I'll put it up later. Matthew's, for people, if they want to check something, they can check it. Okay, so then, all right. So we are very happy to have Shiva and Matthew, who will be speaking on their recent preprint with Carl, and it's on small ball probabilities. Okay, Shiva, over to you.
Okay, thank you. Thank the organizers for inviting me. So here's the, so I will give a preview of what is to come in Matthew's talk, or what I think a preview is. So I will begin with a description of the small ball question. So this is a classical question. It's been around for many years. So the question is the following, that so formally, if you phrase it, so let xt be a stochastic process. So again, as of now, I'm not specifying anything about the process. Could take it any random process that you feel like. I've specified Euclidean space, but you could do anywhere you want. And then you fix a capital T positive. And the question is, the small ball probability question is the following. Question is the behavior. So you look at the chance, the probability that the process until time t, so in absolute as in norm, in whatever norm RD is less than epsilon. You try and investigate this probability as epsilon goes to 0. So I should say is the study of, let's say. So that is the small ball probability question. So what happens to this probability as epsilon goes to 0? So maybe I'll just move this across a little bit down. Question is clear. So that's the question. So what happens to this probability as epsilon goes to 0? So a couple of initial comments. The first comment is that this is typically hard to do. In this generality, it's almost impossible to solve. Typically hard to do for most people. Some people have some. There's some very interesting papers in this area. This another thing is a fact. This not an opinion like the first line, is that there is no general theory available. Though there are several attempts at prescribing a theory for this question, there are no general theory. So I will explain in this talk. There's a connection to this large deviation theory, which is different from the small ball probability question. So that's the question. So now, before I sort of do in any generality, let me just consider an example of a specific process. So let's consider X to be Brownian motion. So that's a sort of well-known process. So X is Brownian motion, and I'd like to understand the same question: what happens to this? So this is very well understood. It's a very old question, probably the only process for which it's kind of completely answered. So the most complete answer, or I should say the entire panorama, is given by this paper by Mogilsky, which is often quoted. And the idea is that they obtained, of course, it's obtained in stages, but the final result is the following: that the limit as epsilon goes to 0, epsilon squared log of the probability that the sup of s less than or equal to t modulus of xs less than, this is in one dimension, so let's say in R. So let me just make it less than epsilon is equal to minus pi squared by 8. So it's a very precise result. So very detailed analysis of what happens to this. So this, maybe this t, I'll just, since I fixed my capital T, I'll just keep my capital T. So sort of a very uniform, sorry, and Mogilsky result, I think t was equal to 1, so I just put as 1 here. So that's the complete answer to Brownian motion in time 1. And of course, this tells you a lot. So what does it tell you? It tells us that that the chance that Brownian motion, Brownian motion in the interval 0, 1, mod xs less than epsilon. So if, what is of the order? The order is on this side I have e to the minus some, let's say c3 pi squared by 8 epsilon squared, and on maybe I multiplied by a c4, and I get a c1 c2 on this side. c1 e to the minus c2 pi squared by 8 epsilon squared. So for some c1, c2, c3, c4 positive constants independent of epsilon. So this is the basic sort of understanding that this probability decays in this fashion as you go towards 0. It's a nice result. So that broadly is the first well-known result that I'll discuss. I won't discuss the proof of this particular result, but I'll try and towards the end of the talk, I'll try and give you sort of the pink diagram, the purple diagram, a proof that we will use for the SPD talk that Matthew is going to discuss. So now let me just sort of give some connections for this question with other.
Shiva, just to interrupt, there are two questions, just clarifying. X0 is 0.
Right.
Or that Matthew has said yes.
Yeah.
Parthanil wants you to scroll down a bit.
Okay. Is this okay now or not?
Yeah, I think.
Yeah, thanks.
Okay, thank you. Okay. So now let me try and do some connections of this question so that it's sort of clear where the question stands after I've said the results. So the idea is that, see, what were we trying to do? We were trying to understand the chance that the supremum of 0 less than s less than equal to capital T mod xs was less than epsilon. Right? So this is what I called as a small ball question. So now using Brownian scaling, so I'll write it down. I won't explain it properly, but the idea is that if you use the scaling that x of s over epsilon squared divided by epsilon has the same law as xs as long as x0 is equal to 0, this probability, if you use this fact, this probability will imply that the same as the chance that in this large time interval, xs is less than 1. Right. So in some sense, I have converted a small ball probability to confining xs in a range of -1 to 1 for large time if epsilon goes to 0. So that I've just said it in a different way. You can write it as the chance that the exit time of this interval -1, 1 is bigger than t by epsilon squared, where the exit time was going to be equal to the infimum, that is the first time that the Brownian motion exits the ball, or radius 1. Now, if you sort of puzzle on this a little bit more, you can convert it to an occupation measure question. So that's the same as saying that if you look at the chance that you look at 1 over, I have to normalize this by s over epsilon squared. Let's say here I have t. Let's say I put t. Sorry about that. T over epsilon squared, integral 0 to t over epsilon squared. I can find my Brownian motion in the interval minus 1, 1. I look at this event that let's call it, x, so xs ds, that is the time spent by Brownian motion in this interval minus 1, 1 up to time t over epsilon squared as full measure. So that's equal to 1. So they're all equivalent questions. So all these three are equivalent questions. So let me just give some comments on this. So like I said before, this is what I started off with. This is the small ball question. These questions are called the confinement question. That is, you allow time to proceed, and you look at the fact that Brownian motion has to spend time in a certain range for large time t. This is also a well-known question. This is the exit time question, the decay tails of exit time, or passage time as people call. And these are connected to what's called the large deviation questions. These are called the, I'll just call it occupation measure questions. So these are in this, many of you know about this, is the large deviation ideas. So from small ball to large deviation, there's sort of a range in this of questions that they answer, and each gives a relationship to the other. So, and then if you kind of were aware that of Donskoy-Vardhan's work, so you can think of this pi. The way they did it was they got this pi square over 8 constant in the previous result. This is the eigenvalue of the Laplacian in minus 1, 1. So principal eigenvalue of Laplacian in minus 1, 1. Sorry. Let me bring it back down. So I'm going to tilt the slide a little bit so you can see the whole page. I'll bring it down a little bit. So that's the broader connection. So where this theory stands in some sense. So the small ball is same as confinement, same as exit time, and same as large occupation measure. And just one comment, I'll just go back to the previous slide. And then, so I don't know if you can see this now. Let's come back. Yeah. So this pi squared over 8 that came in Mughelsky's result was well known for long time. And then that's sort of this Donskoy-Vardhan's idea. So I should probably cite it as this is Donskoy-Vardhan idea. So
Shiva,
yeah.
This Yogesh had a question. Does Shiva?
Yeah, go ahead. Yeah.
Yeah. So does Mughelsky's result have a pathwise version?
Yeah. No, I don't think so. I don't think so.
Okay. Thanks.
There is so just one thing before I go on. I think since people will sort of, I think I'll write the name correctly. It's Lifshitz, I think. So if you just search small ball on Lifshitz, there's a reference page of all papers in this area till December 2016. So I mean, I'll try and post it in the talk slides after I finish the talk. But if you Google these two things, you'll find this reference list where everything is there. Yeah, I don't think pathwise is known. I don't think so. Okay, so that's broad where it stands. So maybe I'll move on now to the. So how far can this go? So you have this nice results of Brownian motion. So there are actually, and the same question has importance in any other process that you come up with. You want to know how the small ball probabilities are. So I'll discuss a few results, just sort of give an overview of what's going on. So these are results by Talagrand and Bass. That's the only thing I'll focus on. So they are on the Brownian sheet. So this is by this is mainly I'll focus on two papers, Talagrand in 94 and Richard Bass in 88, I think. 88, I'm not so sure. Yeah, 88. Yeah. Very nice ideas. I strongly recommend reading them. So what do they do? So the idea is the following. So what is a Brownian sheet? A Brownian sheet is a two-parameter process. So I'll call it as B of S comma T. So let me take the S as in the interval 0 to T and capital T also in the interval 0 to T. I chose this process because so Matthew will discuss another two-parameter generalized field called space-time white noise. And of course, this is related to that process, but so what properties this process has? The property of the process, it is mean zero. That is, for every time S and T, the mean of the process is zero, the parameter of the process zero. And the covariance is given by BST and BS prime T prime. The covariance is just given by the minimum of SS prime and times minimum of TT prime. And the process is Gaussian. So it's a Gaussian process. It's normally distributed with these means and this covariance structure. Okay, this is what a Brownian sheet is. So it's just a two-parameter Markov process. So Talagrand showed this sort of remarkable result on this. What's going on? Sorry about this. Yeah, thank you. So this Talagrand result in 1994. So what he did was he again did the same thing. He looked at the Brownian sheet, the chance that it will survive within a ball of radius epsilon up to a fixed capital T. So the absolute value of BST is less than epsilon. So that's what he's looking at. The same small ball question, capital T is fixed. So then he showed that this had this kind of deviation from, so remember the Brownian motion was pi squared over 8 epsilon squared. So here also he had a minus C over epsilon squared, let's say C1 epsilon squared. But then this was not enough. So the correct asymptotics was with log of 1 over epsilon, the whole cubed. Something funny was going on there. And then, of course, the lower bound also matched the upper bound. So you had e to the minus C2 over epsilon squared log of 1 over epsilon. Right. So and then he took t equal to 1. So I just put t equal to, the constants are all well matched. So I just put t equal to 1. So this is what Talagrand showed. So something funny is going on. This log is giving you an extra sort of interesting behavior. This log is sort of very, let's say, I'll make it in different colors. So differentiate from the Brownian case. So it sort of tells you that the small ball probabilities can change significantly as the process changes. So it's not. And to show this, this is a soup norm. So Talagrand further showed in the same paper that the chance that the L2 norm, that is if you look at it in 2 dimensions, and you look at the L2 norm of the process, or 11 Lebesgue measure in the square of 0, 1, the L2 norm of the process. So B is real valued, and then BST is on the square, integrate as a function of S and T. The L2 norm in the interval 0, 1 behave like the same way, like e to the sum C3 over epsilon squared, but this factor reduced by a factor. So it became log of 1 epsilon squared. So a little different from the other one. So this is something that Talagrand established. That something different is going on in the soup norm, and he explained reasons. The paper explains reasons why the cube appears, and the technique is also very hands-on. It's a great read. Right. So like I said before, this kind of connected with Bass-88. So Bass had already established the lower bound. So Bass had established lower bound. So this lower bound was already established by Bass-88. So Bass did a very interesting thing. So Richard Bass did the following. He took the following. He observed that, it was a well-known idea, that Brownian sheet has a power series expansion. So you sum over some index m, sum over some other index j's. You have these independent Gaussian random variables, and then you have this integrals of this hard basis. Okay. So I won't go into what these j's are, what these m's are. So maybe I'll just leave the indices empty. So this is like these are IID normal, and this is like integrals of hard functions. Hard basis. So if one, why I mentioned this expansion is the following. If one looks at the expansion and one was to do the lower bound, what one would do is one would separate these indices into various blocks, where each blocks are essentially independent from other blocks, and the correlation structure decays in some sense. And then once one would use that to sort of control the probability that Bass controlled, and that's a very clever way. And interestingly, the motivation for Richard Bass's question was actually statistics. So let me mention that question. So let me mention, I'll conclude this sort of survey with a bunch of applications. So applications of small ball. Of course, I've already told you in Brownian motion the mathematical significance of them in terms of how the question is posed. But so Richard Bass came to this question because he was doing the Kolmogorov-Smirnov test for the following distribution. So he wanted to understand if xk's, k's are IID, uniform, let's say, or IID, let's say, I'll just call it distribution F on the interval 0, 0, 1 squared, on the unit squared, some distribution F. And what he did was he took the empirical distribution. Suppose you look at the data looked like 1 over n, summation k equal to 1 to n, indicator 0s cross 0t, and of xi. Look at this, so xk I should say, sorry about that. Look at the empirical distribution function. Then it's well known that root n, this sort of asymptotic holds, root n of fn minus f converges to the Brownian sheet in law. So B is the Brownian sheet. And in statistics, one uses fn to understand f. So what happens is that on the right hand side, you would use this expression on this hand side to discuss the power of the Kolmogorov-Smirnov test that just compares the distance between fn and f. So I'll just call it KS test. On this side, you have the same thing can be phrased as a small ball probability for the Brownian sheet. So this is how Bass sort of came to this question and had a detailed analysis for this. So this is one application. The other application that both Talagrand and Bass did was I will not go into this. They presented a new proof or a very fine asymptotics of the law of iterated logarithms for Brownian sheet. That also follows quite, I won't go through the proof, but follows quite easily from the small ball, if you have exact asymptotics on both sides. I think the lower bound is enough for this, but anyways. And of course, the next one is a simple application of the Girsanov theorem, which we also use in our work that Matthew will describe. It'll give you a simple support theorem for the Brownian sheet. If you don't know what a support theorem is, it just identifies what class of functions, deterministic functions, are close to the Brownian sheet. So what you would do is you would take a fixed function phi st, and you would try to find the chance that bst minus phi st is smaller than epsilon, and you take the supremum for s and t in the unit square. And you try to investigate what this question is as epsilon goes to 0. And for a suitable class of field. and that's called the support theorem that Matthew. It's a small application of the small ball. So we just lift the thing. So the whole page is on one slide. Very good. So you can see the whole slide. So I just began with Talagrand's result, which is a very sharp result on the Brownian sheet. And this log 1 over epsilon cubed is a very interesting factor that comes on both sides. There's an explanation in the proof why it comes. And it's unusual. It's only in the soup norm. In the L2 norm, that's not the case because there's only a square on the right-hand side. And this was a continuation of result by Richard Bass, where he showed the upper bound, the lower bound, sorry. Lower bound. And the motivation for studying the lower bound was the two questions that I've said. One was this Kolmogorov-Smirnov test for random variables on the unit square, and the law of integral logarithms. The support theorem application was fairly well early known. Very good. Okay, so now
Shiva, hello. The L2 norm is less than the sup norm, no? So yeah, if L2, okay, so
that's
yeah.
okay. It goes right way, I think.
So yeah, because the top probability, if you can you just go up?
Go ahead, let's go.
Sorry about this. Yeah, I see. Okay, so the probability for the sup norm is log 1 over epsilon cube. I see.
Correct.
Whereas for the L2 norm, the probability that it's less than epsilon should be larger because L2 norm is less than the sup norm. Yeah. Okay. Thanks.
Yeah, it goes the correct.
But there's no lower bound, right?
No lower bound. Talagrand norm. I think it's still wide. I think there are estimates nowadays available, but they don't match. I don't think they match.
And Shiva, the limit of the Kolmogorov should be a Brownian breach, right? Because
exactly.
So,
you're right. So I should just put a quotes here. So I don't want to. I don't want to go exactly with that.
Right. And that's what Sikant wrote in the chat also.
Yeah. I just wanted to.
Thanks.
I don't want to get into a more complicated object as well.
Right. Thank you.
Yeah.
But one can go from one to other in terms of these small word problems.
Exactly.
Good. Thanks.
So I'll conclude my last 15 minutes with a proof of a partial result for Brownian motion, which of course there are many proofs, but I will write a proof that kind of mirrors the proof that Matthew will discuss for the generalized for the SPD with multiplicative white noise. So I'll just do a proof for Brownian motion. It's not as sharp as Mogilsky's result, but so it's just I'll just call it a small ball estimate. Mogilsky's result is published in an obscure paper, published in an obscure journal. But the paper is available. Shrikar sent me a PDF. If anybody wants, you can ask Shrikar or me. You can share the PDF with you. So the upper bound. So I want to know how large the probability of Brownian motion can be within a ball of radius epsilon. Up to a time. Yeah.
It might be better if you switch off your video. Your voice is breaking now and then. And
okay.
When video is. Okay.
So this is less than epsilon. What is the upper bound? I want to get an upper bound for this, right? So I already know the answer. I want it like some constant over epsilon square. So let me see how far I get in 15 minutes. So what I do is that the trick is to use Brownian scaling and cleverly divide the interval 0t into sort of accepted partitions where you can apply the Markov property and close the proof off. So let's see. So what you do is so let's see, let me write the broad idea. The broad idea is to partition intervals, partition 0t into intervals of length epsilon squared, intervals of length epsilon squared. That's one thing. The next thing is that use Brownian scaling. And the last thing is you use Markov property. So there are three things one has to use to sort of to try and show this idea. So the idea is that how do you do this in a so this is for both the sides, but anyway, the idea. So what you do is you take these points pi. So pi, you call them I times epsilon squared. So should I say epsilon squared, epsilon squared, epsilon squared, and then you take I equal to 0, 1, 2 up till this point t by epsilon squared. So that's the key points that I pick in the interval 0 to t to give me the correct upper bound probability. So the first thing you observe is that the chance that Brownian motion stays in this interval 0 to t is going to be less than the chance that the Brownian motion at these points pi are less than equal to epsilon for all I equal to 0, 1, blah, blah. So that's just a sort of a standard result, right? So it's just if the right hand side happens, then if the left hand side happens, it doesn't mean the right hand side, but the right hand side happens, it means. So it's sort of a simple bound. But then what I do is now I define these events capital Fi to be the chance that at this time point pi, my Brownian motion is less than epsilon. So I look at these points. So now it's a standard sort of a probability idea that you can condition on the previous Fjs and use the fact that this person is just going to the product k equal to, let me call it j, let's say j equal to I think 1 to t by epsilon squared, probability that Fj, sorry, this is Fj conditioned on the chance that the previous guys have happened. So it's I equal to 0 to j minus 1 f sub I. This is a standard probability inequality. This is equal to this. Right? So that's standard. So once you do this, let's try and do estimate. Let's try and do F1. So what's the probability of F1? That's the first term. So let's say again, let me just do in this case, let me just do the fact that mod B0, let me assume mod B0, I don't think it's 0, I just assume it's less than epsilon. It's in this ball. And let me see how to do this. So probability F1 is what? Is the same as the chance that Brownian motion starting at x is some element, x is equal to B0, let's say, just some element in the unit ball, in the ball of it is epsilon. The chance that P1 is what? BP1 is B of epsilon squared is less than epsilon. This is what I want to calculate. So it's a little bit of a thing. And you know that this guy is always going to be less than equal to the sup over mod x less than epsilon. You take all starting points. The chance that x is, Brownian motion is starting at x is less than epsilon. So if you get a handle on this, on this probabilities, then I have a handle on the small ball. Right. So if I know F1, then I'm already in good shape because I can use the Markov property to control everybody else after that. So how do I do this? This is simple. Again, you think of this as sup over mod x less than epsilon, right? Starting at 0, the chance that mod x plus b epsilon squared is less than b tilde epsilon squared is less than 0. But what is b tilde? B tilde again is a Brownian motion, but b tilde 0 is 0. That's what it is. So once you have this is the various ways of doing it. You can do. So I will not do the whole proof because I have 10 minutes left. So I will give it as a small exercise. So there are two approaches of doing it. One is you can see that this probability, because this B epsilon squared is Gaussian now, beta is normal random variable. You can see that this probability is maximized at x equal to 0. Okay, that's one straightforward at x equal to 0. At x equal to 0. That's one way of doing it. Another way of doing it is also, if you don't want to use this normal density and do this, another way of doing it is this way, in the sense that you can do two cases. One is you think of the case 0 less than x less than epsilon as one case, and minus epsilon less than x less than 0 as the other case. And then in both these cases, you use the symmetry of Brownian motion. So symmetry and scaling to get that any of the probabilities are bounded by probability that Brownian motion starting at 0 is between -1 and 2. Okay, so you can actually check that. This calculation is straightforward, and you can just do it. And this is some quantity eta. Okay, so you can do it my way or that way, whichever you want. You get a probability eta. So once you have this, so what does this mean? This means that the chance of F1 happening is less than eta, and by the Markov property, everybody else is also less than eta. So by it's a standard calculation, which I will not do it. By Markov property, this is true for all j. So probability of fj given intersection I equal to 0 to j minus 1, fj is also fi is less than equal to eta. This is standard. So once you have this, you have how many of them in this? If you go back to the slide, let me just come back in a second. You have t over epsilon squares of these people, all of them less than eta. So you know that immediately. You know that the chance that soup of 0 less than s less than t or less than capital T mod bs is less than epsilon is less than eta to the power some constant by epsilon squared. Eta is less than 1, so this guy is going to be some c2 e to the minus c3 by epsilon squared. So let me just bring it up like this in one slide so you can see the whole proof. So that's formally the idea. So I've given most of the steps, but the proof is fairly straightforward. So that's broadly the formal proof of this whole calculation. So all you have to do is cleverly choose these points that are spaced in this form I epsilon squared, and essentially it's scaling and Markov property that gives you the answer. So now let me try and give you a flavor of the lower bound. I have about 8 minutes left. I think I should be able to do it, at least the sketch of the lower bound, if not the whole proof. So lower bound also is again the same way. You have to make sure to use Brownian scaling and Markov property to do the exact answer. So it's lower bound. So again, what I want to look at the chance that Brownian motion in an interval of length capital T, a time interval capital T, mod bs is less than epsilon. I want to know what the lower bound is. And if the lower bound and upper bounds match, then I'm on my way. So here what I do is I take the same PIs, but I have to do a little bit more. There's a little bit more non-trivial argument. So what you do is you consider intervals. You consider intervals of length epsilon squared. So you start at I epsilon squared and maybe go up to I plus 1 epsilon squared. And you take this for I equal to, since I'm starting at I go 0, 1 up to this T over epsilon squared minus 1. Formally, I mean, this was some gymnastics I have to do at the end, but broadly, this is what I do. I'll split the interval 0t into these intervals. Then, before I had these just singleton points, but here I have to do something differently. Here, what I do is I think of my events AI for each interval I in the following way. That is, I let my Brownian motion always be within a radius epsilon throughout the interval. So I epsilon squared to s less than I plus 1 epsilon squared, or less than equal to, let's say I can put, in this entire interval, I want Brownian motion to be within radius epsilon. Okay. And then, but the crucial thing is, at the end point, I want it to come inside, a little bit more inside. So at the end point, that is at by I epsilon 1 squared, I want the Brownian motion to be within radius epsilon by 2. Okay, so the idea is clear. So in the entire interval, so let me, there's two events. In the entire interval, I want the Brownian motion to be within epsilon. So it's in the range minus epsilon to epsilon. So that's where the Brownian motion can go around, can go up all the way around. But when I come to this to the end point, I want it to come inside a range of minus epsilon by 2 and epsilon by 2. So this is at this point, and then at this point also I want it to be starting inside this thing, and then it should also end at this point. So this is I epsilon squared, and this is I epsilon plus 1 epsilon squared. This level is minus epsilon, this is minus epsilon, this is epsilon by 2 minus plus epsilon. So maybe I'm running short of time, but I'll try and see if I can develop a proof of this. So it's the same way. So it's the same, you can apply the Markov property. It's enough to show, so again, the same argument as before, it is enough to consider, enough to show probability of A0 is bigger than some C1 e to the minus C2 by epsilon squared. This is just a same argument as upper bound. So same as upper bound. So the same thing. So you'd establish this guy. So, but this person is what? This person right here is what? Is the chance that, so X is, I'll start B0 within a ball of radius epsilon by 2. So here I have X is B0 and I have P sub X. And what is A0? A0 is the chance that supremum from 0 less than S less than epsilon squared modulus of BS is less than epsilon. So it stays in this.
Shiva,
yeah.
The lower bound, you just want eta? Greater than or equal to eta?
Sorry, thanks. Thank you. Delta, I should say. Thank you. Sorry. Delta, some delta. That's all I want. For some delta 0. Thank you, Matthew. So I need this A naught bring delta, and probably what is A0? A0 bring 0 epsilon squared, and this is modulus of B epsilon squared at the end point has to be within epsilon by 2. Okay. So that's what you have to establish in some sense. So this requires an argument. I'm out of almost, I have 3 minutes left. Let me see how much I can show this. So let's do a simple one. A simple one is the following, that that let's say X is equal to 0. Okay, so say X is equal to 0. I start in the middle. Then this probability is at least the chance that the Brownian motion starting at 0, supremum 0 less than S less than epsilon squared modulus BS is at most epsilon by 2. So it stays epsilon by 2 always. So it's upper bounded by this. So lower bounded by this problem. So this simple calculation for X equal to 0. But this by Brownian scaling is always bigger than delta. So this is bigger than some delta by Brownian scale. Because I divide time by epsilon squared, I have interval 0, 1, and I have only half on the right-hand side. Just some delta positive. So for general case, you have to use a Girsanov theorem. So for general case, what you have to do, you have to use a Girsanov transformation. So for general case, so I won't do the entire proof, but I'll just give a sketch in the last 1 minute. For the general case, what you have to do is you take B tilde S to be equal to BS plus SX by epsilon squared. Okay. So now you take a measure Q under the Girsanov transformation. So dQ by dP is equal to exponent of minus X by epsilon squared b epsilon squared plus minus 1/2, or let's say I should say, since I have 0 to t, I'll just write it as 0 to epsilon squared b dbs, just to make the Gaussian transformation clear, minus 1/2 epsilon squared or minus x squared by epsilon squared, 0 to epsilon squared of ds. So you do the Gaussian transformation, and then you work with q and estimate q of a naught. And that's the same calculation as x equal to 0 to get q of a naught is bigger than delta. Okay. So once you do this Gaussian transformation, all you have to establish then is that the second moment of this of the random derivative is kind of nice, is nicely behaved. It's like C1 and C2. And that's easy to see. It's an exponential martingale. It's very well behaved. This is trivial to see. It's easy to see. And once you have these two steps, this and this will definitely imply that P of A naught is, let's call this delta 1 for some delta 1 positive. And this will imply that P of A naught is bigger than delta. I'm sorry, I was a little rushed in the last part, but the broad idea is the following. The broad idea is essentially like you have to sort of partition the intervals into the correct scaling length depending on the process. So Brownian scaling length is given by this epsilon squared scaling. Once you have that, the whole proof works through automatically. There's the sort of standard ideas to get the idea. Okay, maybe I'll stop with that. Thank you. Yogesh, can you hear me or not?
Hello.
Yeah,
I think people can unmute themselves, and we'll give a round of applause to Shiva and then some questions. Okay, so anybody has any questions, please feel free to unmute yourself and ask. And before that, Shiva, one question asked by Kaushik in the chat in the middle. I think it was not responded to. Kaushik, I think you can maybe ask yourself. Can you see the question, Shiva? It's,
let me see a question. Where's the question?
It's around 2:42 p.m.
2:42 p.m. Let's see. 2:39. I see. Kaushik, I don't see Kaushik.
Okay, Ram. So if we know the torsion function u such that Laplacian u is equal to -2 with u equal to 0 on the boundary, then the bounds on for the exit time are immediate.
Yeah, I think these are standard facts. Right? This is a different proof. I think that's one way of doing it. I'm fairly sure. I don't understand -2 yet, but broadly that's correct. Oh yeah, 1/2 Laplacian is -1. I think that's correct.
Okay.
Yeah. This is just a proof. It's not the proof. It just I gave this proof because it motivates the proof that Matthew is going to do.
Okay. Any other questions?
Yeah, perhaps can I ask one?
Yeah, sure.
So Shiva perhaps answered the question, but anyway. So how general is the proof? I mean, it can go through for any self-similar process with Markov property.
The scaling idea is kind of. The only thing is that I was a little glib in this following. The Markov property will ensure this product, like this product term right here. Let's say the product.
Right. Then you won't have product, something else.
You have something else. Then you have to work with that. You
have to work with conditioning, perhaps.
Matthew will have some correlations. He will show you how to fix that correlation.
Right. But self-similarity is needed, at least, to carry over this proof.
Self-similarity means in what sense?
You're doing this. I mean, Brownian scaling.
Yeah, Brownian scaling. Brownian scaling is scaling is important. If you don't have scaling, this proof will not work.
Scaling is self-similarity.
Crucial, very crucial. That's correct.
Thanks. Very nice talk, by the way, Shiva. Thank you.
Okay. Any questions? And anyway, people can continue asking, and other people who are interested can make tea or coffee and have cookies. We'll meet in 10 minutes time, 3:30.
Yeah. Yogesh, I'll just take a little break. I'll come back at 3:30. 3:25.
Okay, fine.
5 minutes break.
At 3:25. Okay. So Shiva will be back at 3:25. And among others, yes, people can discuss among themselves. So, yeah.
Thank you.
Have coffee.